This conference will now be recorded.
Very good evening, students. Today we'll be continuing with the ray optics chapter itself. So yesterday we had discussed somewhat about total internal reflection, TIER. I think it should not be TIER, total internal reflection, TIR, sorry. So TIR, we had discussed yesterday some natural phenomena. We have discussed only one out of few more. Due to some technical issue, I had to conclude, or I had to interrupt in between. So I'll just today discuss few more phenomena related to total internal reflection, TIR, and then I'll just move on to the spherical lenses, and we'll discuss the terms related to spherical lenses, and we'll go for the refraction through spherical surfaces. We'll discuss how refraction happens through spherical surfaces. Okay, so I'm not repeating because we have a lot of content to cover today. I'm not repeating these things what I have already discussed. Okay, so I'll just go to this fiber optics. So this is another application of this total internal reflection phenomenon. Okay, so you know what, see, this is a typical fiber optics, like a typical optical fiber which is being used in the communication system. So this is a cable, like from outside you see just the black cable. Okay, this is actually the outer covering. Okay, so inside there are actually two layers of, like the cylinder has two layers. If you see, this look like this part. Okay, but you know, you will have two transparent layers in between. One is called cladding, another one is called core. Generally, if we take the cross section of this optical fiber, you look like this. Okay, that will look like this one. You can see this part is called cladding, the outer part, and the inner part, this is called core. Okay, this is called core, and core has suppose refractive index n1, and the cladding has refractive index n2. You know, this n1 is always greater than n2. Okay, so an optical fiber is a very thin, long strand of made of glass or quartz surrounded by a glass coating of slightly lower refractive index. That means, you know, this can be high quality glass. This inner part, okay, inner part means core has to be high quality glass, okay, or quartz made of quartz or glass, and just on top of that there will be a coating, or there will be a covering of glass. Okay, that is called cladding. This cladding has less refractive index. Okay, so what is this used for? It is used as a guide medium for transmitting an optical signal from one place to another. Okay, generally uses of this optical fibers or applications of optical fibers are being asked sometime. And see, what is the working principle here? This is the total internal reflection. Working principle of generally in JEE advanced this optical fiber is to come. So working principle is TIR, total internal reflection. Okay, total internal reflection. And so total internal reflection means, you know, mu is equal to 1 over sin IC, right? Sin IC. So here you look, the refractive indices of this core and cladding are such that if ray just enters through this opening, okay, it will surely have angle of incidence. Here it is theta c. So angle of incidence I will be always greater than theta c. And at the interface of this core and cladding, there will be a repeated total internal reflection, and that's how light actually propagates through this tube. Okay, or yeah. So, but you know, there is a limit to the angle, at which it should enter with the axis of the fiber. So the angle, the maximum angle, see this is denoted here alpha. The maximum angle, that means, you know, if this angle is alpha, and from with the axis other side also this angle is alpha, that means, you know, there is a cone kind of that, and within this cone, if the rays are entering to the fiber optical fiber, then that will suffer total internal reflection. I'll just draw the cone for you. Okay, so this is the cone. This is the cone. So the light rays which are entering through this cone will definitely suffer total internal reflection, and that signal will be, that optical signal will be transmitted. In general electrical signal is actually converted into optical signal in the modern communication system, and then it is actually reconverted into electrical signal, and from there maybe some other form. Okay, so this is what is done in modern communication system. In many, like if you go to the advanced countries, they are not using the metallic wire for even electrical communication. Electrical communication also are being done in some places through this optical fiber, but most of the cases in our country, optical fibers are used in communication system, television, etc. Okay, television cables are made of this optical fiber. Moreover, these optical fibers are actually used in various showcase material, to make showcase materials also. Okay, so this angle alpha, this is actually the angle, sine of this angle alpha, the maximum angle within which, or maximum angle with the axis of this optical fiber. Okay, so sine of this angle alpha is actually called numerical aperture. Sometime numerical aperture will be asked to find out. So you have to find out sine alpha. Sine alpha means square root of n1 square minus n2 square. This is actually called numerical aperture, and twice of this alpha is called angle of acceptance. That means the ray which has, like light rays or the signals, optical signals, which has to be transmitted through this optical fiber, must be within this angle. Okay, this angle 2 alpha is called acceptance angle, and numerical aperture is sine of alpha, and that could be found out this as square root of n1 square minus n2 square. So this is what is small information about optical fiber, and as you know, this works in the principle of TIR. Okay, now we'll see one good application of this internal total internal reflection in the nature. You know, if you have a luminous object is located at the bottom of the big pool of liquid of refractive index mu, the depth mu and the depth is h. I'll just show you the figure here. So suppose this is a big pool, and this here at this particular position there is a luminous object which can produce light. Okay, the object is emits rays which are going upward, right, in the direction upward direction, so that, and you know, surprisingly, you'll see this is a point object. It is actually sending light all the way, right, all the way it is sending light, isn't it, light rays. But from the top of the, like from the top surface, if we look, we'll see only a bright circular patch like this, okay, in the water surface or upper surface. We'll see even though this source is sending light all the way, like all over symmetrically. If we think this is a point object actually sends light in all direction, okay, and still we'll see a only circular patch on the surface of the water. And see, these places will not see any light, no light here, no light, okay, no light here, also no light, okay, no light, only light, as if light is coming out from here through this circular patch, okay. So this circular bright patch, sometime numerical problems will come to, like there will be, see this height, depth will be given, mu will be given, so mu will be given, depth will be given, depth is this h, okay. You have to find out the radius of the circular patch. In some cases you have to find out some relationship between mu, h and r, which we are going to discuss today. See, the relation we have to establish now related to this question is, okay, so sometime they will ask you to find out area of the patch. So area of the circular patch will be pi h square divided by mu square minus 1. This you have to find out, okay. This is, first of all you have to find out what is the radius, then you have to find out the area of the circular patch. So this kind of question will be asked, okay. We have to just find out, okay. So radius will be actually h by square root of this, okay. We have to show that, okay. How do we get this, okay. All right, we'll just do this now. So the question, let me read the question fully. So that a circular patch is formed at the surface of the liquid by rays which are refracted into the air. What happens to the rays beyond the circle? Determine the radius and area of the circle. So this is our agenda with this particular problem. Let us try to solve this, okay. Let me just clean everything. Okay, maybe I'll make this figure a little smaller so that I get a little more space. Okay, fine. So let us see, this is S, okay, and let us take the radius of this patch to be small r. Mu is the refractive index given, r is the radius of the circular patch, okay. H is depth, so this is refractive index of liquid. Let us not take by default water, maybe it is water, I don't think. Yes, it is given as liquid, okay. It can be water also, doesn't matter. And h is the depth, okay, fine. So why this happens, first of all, let us understand why this happens. So this is the source from where I'm just taking two representative ray. See, the refraction happens here. So this is air and this is the liquid. So light is refracted from denser medium to D to rarer medium, right? And there is the possibility of total internal reflection. Okay. And see how we see patch. See the ray which are below critical angle of incidence, the rays which incident at the interface with an angle of incidence less than IC, they will be directly refracted. Okay, but when the angle of incidence, this particular angle will be exactly equal to IC of the interface or IC of the medium here, then what will happen, you know, the refracted, see, angle of refraction will be 90 degrees. See, this is the 90-degree angle of refraction, and the ray will be actually just passing through the surface. It will be passing through the surface or grazing the surface. Okay, grazing the surface. So the only ray which we will be able to see or which will come to our eyes are these rays which are passing through this circular patch. Okay, because see, this is 3-dimension. You can see this is cone as a cone. Okay, so I have taken rays, two rays, representative rays, which actually incident at this interface exactly at the critical angle. I see this is the critical angle. So if this is critical angle IC, so this also will be IC. Here, similarly for this side also, if this is IC, then the ray will be actually grazing the surface, and this IC means this is also IC. Now from here, look, we know this formula, right? Mu is equal to 1 over sine IC from the Snell's law, sine IC. This we know. And further, what we know, what we can find out from here, this is actually CR, this is H. So actually we can find out what is sine IC here. Sine IC will be equal to sine better to find out tan IC, okay, instead of finding sine IC, because we don't know this. In fact, we can find out. Yes, sine IC also we could find out. Let us find out sine IC. Sine IC will be perpendicular by this ASB. ASB is the hypotenuse. So hypotenuse will be actually square root of r square plus h square. So this is one thing. This we can find out. But better to go with tan IC. That would help you. Tan IC means perpendicular by base. Perpendicular is here r, base is h. Okay, now it is easy actually. Let us not go with this. So tan IC we have found out. So tan IC means sine IC by cos IC equal to r by h. In fact, we will get the same thing if we go for. Okay, so sine IC we know already. We can just put the value. Sine IC means 1 by mu. So we can actually write r by h is equal to 1 by mu cos of IC. Okay, so we need to find out. See, what is this cos IC then? 1 over mu cos IC means square root of 1 minus sine square IC. Okay, sine square IC. Okay, look, I'll just take help of this place, this small place. So R by H is equal to 1 over mu, and square root of 1 minus sine IC means 1 over mu whole square. So you get, see, I'll get here, mu will be going up, 1 mu is down, and in the numerator there will be mu square minus 1. Okay, this mu will cancel each other, so R will be H divided by square root of mu square minus 1. I think I have made it very messy. You can just go with very clean things. Okay, so what we have done, you just look, see mu, this is at critical angle, this you know already from the total internal reflection. Okay, and see this condition we found out here, R by H is equal to tan theta. Tan theta means what? Sine IC by, sorry, tan IC. Okay, this is equal to tan IC. Tan IC is equal to R by H. So R by H is equal to sine IC by cos IC. So sine IC means 1 by mu. So that is what I have written here. And say cos IC means square root of 1 minus sine square IC. Sine square IC. And sine square IC means 1 by mu square. Okay, sine square IC. So from there, if we just simplify, we'll get R is equal to H by square root of 1 minus mu square. You can memorize this formula to easily find out the answer. This is R. This is the radius of this patch. Okay, radius of this patch. We have got the radius of this patch. Now what to find out? We have to find out the area. Okay, so we have, I'll just clean this portion. I'll clean this portion. I think I'll clean everything. So what we have got, R is equal to H by square root of mu square minus 1 we have got. So area will be pi R square. So pi H square divided by mu square minus 1. Okay, so this will be the area of the patch. So guys, you have, I think you have understood this, how we have done. So see, there is another point here to answer. What happens to the rays beyond the circle? See, now any ray beyond this will be actually having angle of incidence greater than IC. If that is happening, then it will actually be totally internally reflected to the liquid itself. Okay, it will go into the liquid itself after total internal reflection like this. Okay, hereafter, say beyond this circular patch, all the rays will be actually totally it will be reflected totally. Okay, and it will go into the pool itself. Okay, so this is one thing. Now we'll just go to the spherical lenses. So we have seen spherical mirror. In that case, we have already learned a few terms like focus, principal axis, then object distance, image distance. These are common for the case of lenses also, but here in case of lenses, there will be, lenses are transparent. Okay, so a lens is a piece of refracting medium. Actually, there will be refraction. In mirror, spherical mirror, what was happening? Reflection was happening. Here, refraction will happen. So lens is a piece of refracting medium bounded by two surfaces. It is actually, if I just draw, it is bounded by two surfaces, and one among them must be carved. Okay, one among them, two surfaces, one among the two surfaces will be carved. Okay, at least one of which is carved. Then it will be said as spherical or lens. Okay, spherical lens. All right. So now, so it is a refracting medium. Okay. Now there are two type of lenses, mainly two types, major or mainly two types. One is actually convex lens, okay, and other one is concave lens. We'll discuss them in the next here. So what is a concave lens and what is a convex lens? A convex lens is one whose middle portion is actually thick but the edges are thin. Look, this is a kind of convex lens. This is convex lens, but there, see, in this case, in case of convex lens, either both refracting surfaces, there are two refracting surfaces. If I give a name A, B, C, and here I'll write ADC. So there are two refracting surfaces. One is this ABC, and another one is ADC. When both are spherical, okay, then automatically the middle portion will be thicker and the edges will be thinner. Okay, and in this case, you know, in this case, when a parallel beam of light gets refracted, they will converge at any point, at a particular point on the principal axis. They will so that's why these convex lenses are called converging lenses also. Okay, converging lenses. So the lenses which converge the light can be another definition of convex lens. But convex lens can be of different type. You can see convex lens can be such that, okay, so I think I'll come to that point. See this, I'm saying this is spherical lenses. Okay, spherical lenses means, you know, the lenses are actually part of some spherical transparent, a part of, see, a refracting surface will be part of a single spherical object. Okay, transparent spherical object. I'll draw it properly. So spherical lens, in case of spherical lens, the refracting surfaces are part of two spheres. So this part is a part of this sphere. If I say this is sphere 2, this is sphere 1, so this refracting surface, this one is actually a part of the sphere 1. Okay, so that's why this these refracting surfaces will have a radius of curvature, but if they are part of the spheres which have the same radius of curvature, then both sides, both will have the same curvature. Like in this case, it is arbitrarily taken, so radius of curvature for both the surfaces is not equal. See, I'm sorry, this will be written 2, this will be written 1. So this radius of curvature is R1, radius of curvature of this refracting surface, and radius of curvature of this refracting surface is taken as R2 in this direction. Okay, R2. Okay, so in case of convex lens or converging lens, refracting surfaces may not have the same radius of curvature, but if there are two such convex two such spherical surfaces, then they are called biconvex lens. Both the surfaces are actually convex, then this is called actually biconvex lens. When both the surfaces are having the same radius of curvature, then that particular convex lens will be called as equiconvex lens, as you see here. See, for the convex lens, if one surface is convex but the other surface is plane, then it is called plano-convex lens. Okay, convex lens has various. See, if among, like, between the two refracting surfaces, one is convex, another one is concave, then it is called concavo-convex lens. Okay, so this is about convex lens. In general, convex lens will converge the light at the focus of parallel light, obviously, after refraction to the focus. Okay, to the focus. That's why these concave lenses are called in general, sorry, convex lenses are in general called converging lens. Okay, now we'll go to the diverging or concave lens. So in this case, you know, the middle will be thinner or the center will be thinner compared to the edges. So what it does, it actually diverges the light after refraction through it, and it has actually virtual focus. It has real focus. This is virtual focus. We'll see what is called focus and all. And in this case also, you can have this biconcave lens, then equiconcave lens, plano-concave lens, then concavo-concave lens. Okay, concavo-concave lens. So there are different types of lenses. In case of plano-convex lens or plano-concave lens, the plane surface will be always having the its refractive index at infinity. Okay. Now, in case of diverging lens, okay, we'll see during discussing about focus. So different terms related to lens. So these are, as I was discussing, there are many common terms with spherical mirror. I think you may not be able to see the figure fully. I'll just make you see this. All right. So you can see I have a figure over here with which I'm trying to give the overview of different terms we'll be using in studying refraction through lenses, spherical lenses. As I was saying, the spherical lenses are part of two different spheres. Okay, so there are two radius of curvature, like radius of curvature. See, these are two center of curvatures, okay, C1 and C2. If we join these two center of curvatures and extend the line, this line is called principal axis, similar to mirror. Pole and focus, if you like pole and center of curvature, if you connect and then extend, that is called principal axis. In this case also, if we connect the C2 and C1 for both the spheres and then extend, that will give you the principal axis. Okay, this is same for the definitions is same for both the concave and convex lenses. Okay, now radius of curvature, as I said, these are actually radii of the two different spheres. And look, in this case, we'll discuss the sign convention. Sign conventions are same as the mirror. case of like as we have learned in case of mirror, the sign convention will be the same in case of lenses also. That means the ray, the distance we measure along the direction of the ray will be positive, and opposite to that will be negative. The height we measure from the principal axis to the like above the, so the height we measure above the principal axis will be positive, and height we measure below the principal axis will be negative. All right. Optical center is actually the geometrical center of the lens. Okay, geometrical center of the lens, that is the optical center. Okay, these are points we had to discuss. See, in case of, see, if this is the surface, then it has its, suppose this is R1, this is positive radius of curvature. If I have this, then it has radius of curvature, this one we have to measure in this way, opposite. So this will be R2 will be negative, but obviously that depends on the given problem, and also that depends on the name you give, R1 and R2. Okay, we'll just go to the sign convention quickly. Oh, okay, the terminology. Okay, we have learned already principal focus, optical center, radius of curvature, center of curvature. Now one important point here is the focus. Okay, so in case of lenses there are two focus. Actually singular form of focus is focus, and when it is plural then they are called foci, F-O-C-I. Sometimes people say foci, okay, or foci. Okay, sometimes they are pronounced as foci, foci. Okay, so plural form of focus is foci. So there are two foci actually in case of lenses. One is called first principal foci and then second principal foci. You can see here. See, first principal foci is generally defined in this way. If the ray of light coming from a particular point on the principal axis, okay, in case of convex lens, obviously, after refraction, those rays will be becoming parallel to the principal axis. So this point is called then first principal focus. In case of concave lens, the ray are not coming exactly from any point on the principal axis, but if they have they are appearing to come out of a particular point, and after refraction those rays are becoming parallel. So this particular point is called first foci in case of concave. Okay, first principal foci. Now second principal focus is defined in the opposite way, just reverse way. That means the parallel rays after refraction meet at F2, which is second focus. Actually this lengths are also equal, you know. If the radius of curvature are equal, then length are, say, F1 and F2 both are equal in length. Okay, that means, you know, you can use this is a transparent, right? And also the F1 is equal to F2. You can use these lenses from the both side. Okay, from this side, from this side also. All right, so these are principal focus. For a lens. Okay, now we'll just see or learn today's the main and most important topic, that is refraction through spherical surfaces. See, refraction through spherical surfaces can happen in any direction. See, I have a transparent medium, like I'm just looking through a glass. I'm looking through a glass. Okay, so this is glass. Okay, I'm looking through a glass. This is air. So object can be here, and that can be seen from here, or object can be in the air, and the refracted ray may be going into the other direction. Okay, so depending on that, the nature of the images will be different. Sometimes it may be virtual, it may be real. Okay, so maybe, okay, so different cases may come. What we'll do today, we'll take an object in the rare medium and see the image of that object in the denser medium. In this case, see, I have the interface mn. Let us take this nn prime. Okay, nn prime, the whole one. Okay, the whole thing is this nn prime. Actually, this perpendicular is mn. Otherwise, let us take this as p. The center of this is taken as p, and this perpendicular from this point to the principal axis is this nm, is the perpendicular. Okay, and see here, while deriving, see, in this case what we are going to do is, actually we are going to see the relationship between the different refractive indices. Okay, n1 n2, object distance, then image distance and focal length, etc., or maybe radio of curvature. So we are going to derive a relationship among these terms. Okay, among these terms. So here what we are doing, we are taking an object in the rare medium. Here n1 is less than n2. Okay, that means this is actually denser medium and this is rare medium. So if we keep an object in the rare medium and see the image in the denser medium, the image will be actually real. Real means it will be inverted. This will be sometimes reduced or diminished image. Okay, so let us find out what are the relationship between u, v, r, n1 and n2 in this case. So since it is called ray optics or geometric optics, we are going to use just geometric, simple geometric formula, etc. Concept of that. Okay, let us see. Let me just give the name of this particular. See this particular angle. Let us say this point is P initially, and this is M is the perpendicular. This is written here. Okay, so hope I don't have to erase again. So this angle, let us say it is alpha. Okay, and you know this is angle of incidence. You know that this is angle of refraction. Let us take this angle as beta. Okay, and this particular angle let us take as gamma. And see here the image has been formed, right? Let us take that. Okay, this is image I itself. It is written as I image. Okay, all right. So we are just drawing a perpendicular. In this case, aperture is small. Aperture has been taken. So if it is small aperture, then this mirror curvature can be like this. Nm can be taken exactly nm. This is perpendicular to the principal axis. That means nm and np are coinciding with each other. P and M will be coinciding each other. Okay, so now from this figure, if we see the triangle, this N, this is object O, and this center of curvature. This triangle, if we look, let us see what we are getting. See, in this case, this angle I for this particular triangle will be what? This will be exterior angle. So I can write this I, since it is exterior angle, I can write it is to be equal to sum of the interior angle, okay, alpha plus gamma. I hope it is all right for you also. So this is exterior angle, the sum of this alpha plus gamma. For the sake of convenience, we let us not give the angle sign here, otherwise that will take my time. So these are, okay, this is the one. Now similarly, if I take another triangle NIC, look, N, I and C, this angle. So in this case, gamma will be exterior, right? So gamma will be exterior angle, this gamma, because I'm taking NIC triangle. So it will be actually sum of R plus beta. I think up to here you may not have any problem. This I can write as R is equal to gamma minus beta. This is also fine, isn't it? So this is equation number 1, this is equation number 2. Okay. Now suppose rays are paraxial. Paraxial means very near to the principal axis. So all the angles I have taken here are small angles. Alpha, beta, gamma, then R, I, all are small angles. All are small angles. Okay. So now here, if these angles are small angles, then I can write alpha is nearly equal to tan alpha, or sin alpha I can write. Okay, nearly equal to tan alpha or sin alpha I can write. Okay, so look, similarly tan beta, tan gamma is equal to gamma I can write, like tangent of particular angle may be written as the angle itself. So here what I'm trying to do is tan alpha. Let us write tan alpha. Tan alpha will be how much? See, tan alpha can be written as nm by om. Nm perpendicular by base. Nm by om or op. See, m and p are coinciding, so that's why nm by op. Okay, and this is fine. So alpha, this will be equal to alpha as well. So alpha is equal to nm by op. What is beta? So tan beta is nothing but nm by mi. Nm by mi. You can look from the figure. Nm by mi is actually tan beta. Okay. So mi means pi also. I can write that nm by pi. This is nearly equal to beta. So I have got a beta and alpha. Similarly, I can get gamma as well. So I have taken this as alpha, this as beta, this as gamma. IR are already there. So tan gamma is this one. Tan gamma is perpendicular by MC, perpendicular NM by MC, or NM by PC. Now from Snell's law, what you can write? From Snell's law, I can write I sin, sorry, mu, sorry, N1 sin I sin I into sin R. Okay, or so sin could be written as I itself. Now this I and R, we'll just put the value. So this is N1. We'll put the value of I and R. See, I was alpha plus gamma, right? Alpha plus gamma, and N2 was sorry, this is I. I is equal to R plus alpha, and R is equal to gamma minus beta. I think this is the case we have written already. Gamma minus beta, yes. Now this alpha and all we have already written here. Alpha is equal to what? Alpha is equal to Nm by OP. Beta we have written similarly gamma. So from there we'll be directly writing in this equation. Okay, this is N1 into, see, I means alpha. Alpha means tan alpha. Tan alpha means this by this. Okay, Nm by OP. Nm by OP alpha, then gamma. Gamma means this Nm by PC. Nm by PC. Okay, so this side is done. Other side N2 into gamma minus beta. Gamma is again Nm by PC minus Nm by Pi. See, beta is this one, so Nm by Pi. Okay, so now the Nm are common from both sides. From all of them, if we just strike them out, so this will be 1 over OP plus 1 over PC is equal to N2 into 1 over PC minus 1 over Pi. Okay, now if we do further calculations, the further simplification like PC and PC I'll just bring together. Okay, PC and PC if we bring together, what is the case? See, PC and PC, see, this is this PC, this. Okay, so N2 minus, I'll take them there. So this is N1 OP, N1 by OP. I'll write it here. N1 by OP plus N2 by Pi. This has now become N1 by PC. So N2 minus N1 by PC. Okay. PC means what? PC means here. PC means R, right? And this R is positive R. Okay, positive R. So N2 minus N1 is R. And see, OP is what? OP is here actually minus U. N1 is actually minus U. See, N1 by minus U. OP means this distance. Okay, this is U, and Pi is actually image distance, as you see. N2 by N2 by N2 by V. V is taken in the positive direction. Okay, so if we just simplify this relationship, see, then we get N2 by V minus N1 by U, that is equal to N2 minus N1 by R. Okay, so this is what is the relationship we get. So what we get, if this is, see here, if here is the object and here is the image formed here in the denser medium, the image formed. Then we can write, in fact, for common any spherical surfaces wherever the object may be, actually the main formula is n2 by v minus n1 by u, object distance, this is image distance, is equal to n2 minus n1 by r. Okay, so this is actually the formula for refraction through transparent medium or spherical surfaces. Okay, so if suppose the first medium is air, this medium is air, then this n1 will be 1, isn't it? So n2, let us say n2 is becoming n. Okay, let me just write it here. So n1 will be air, so this is like this, and this is n2 minus 1 by r. Okay, let us write this to be n itself, n by v minus 1 by u, this will be n minus 1 by r. Okay, so this is how we have to actually remember the formula for the refraction through spherical surfaces. I'll stop it here for today. Next day we'll discuss similar kind of things, and like say if we keep the object in the denser medium and then see the image in the rarer medium, what is going to happen, etc. we'll be seeing. Okay, and in that case how to take the sign of this, sign of UV, etc. we'll be discussing in detail. So bye for today. Thank you for your attention.